In a previous video, I looked at counting techniques that involved the techniques of the multiplication rule of counting, permutations, combinations, and then permutations of non-distinct items. Now, those situations work with the counting technique type problems when you're asking how many ways you can do like a sequence of events, when there's so many ways to do the first event, so many ways to do the second event, on down for your multiplication. When you're looking at permutations, you have an overall set and you want to know how many different ways you can pull R of those n items, and then also count individually all the placements within that group that you pulled. And then combinations, you have that overall group and you're pulling R items out of the n items, but order arrangement within what you pulled didn't matter. Now, I've put a link to that video in the description of this one in case you would like to go back and review that. In this video, we're going to start by looking at counting technique problems that actually need us to have the multiplication rule of counting as well as combinations, because within the overall set there are subsets, and we want to know the different ways that we can pull some out of the subsets that are specified within our overall set. And then near the end of the video, we will look at finding probabilities of problems that ask us probabilities when there is a selection of subsets out of the set. So let's get started. Counting techniques problems that require the multiplication rule and combinations. Now, I'm going to start with an example that doesn't require us to use this, so we can review what we would do for that, but then start to do a lot of different examples where we do need to use both the multiplication rule and the counting and the combinations. So our first example is an old review one from the other material. So a club's membership consists of 7 men and 8 women. How many different 4-member committees can be chosen? So while it did start by telling me our subsets within it, when they asked how many 4-member committees can be selected, they didn't say my committee had to be made up using so many of the men and so many of the women. It was just overall a 4-member committee. Now, in a committee, none of the members have any jurisdiction over each other. They just go off and they discuss what item that they've been charged to do. So here, I don't have placement within the group mattering, and that's why it's a combinations problem. And it's how many, so it's a counting problem. So this would be combinations of, my entire club's membership is 7 plus 8 or 15. And I'm looking at a 4-member committee, so I'm choosing 4 out of those 15 members. Now remember, I can figure this out either by the formula for combinations or by using the graphing calculators options, or and many times the scientific calculator will have this, to be able to look at this number. From the formula aspect of it, it's n factorial, so 15 factorial, the overall number, divided by your r factorial, so 4 factorial, times n minus r factorial, so 15 minus 4 factorial. Now do what's inside the parentheses first. 15 minus 4 is 11, so I have 15 factorial over 4 factorial times 11 factorial. And then when I'm simplifying this, I'm going to run the 15 factorial down till it hits the larger of the factorials in the denominator. So remember, 15 factorial is 15 times 14 times 13 times 12 times 11 times 10 times etc. Multiplied by all of the natural numbers below it. So start with it and by all the natural numbers below it. But the 11 factorial, I'm going to stay packed together as 11 factorial. In the denominator, this other 11 factorial, I'm going to stay packed together because they both do the 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it's all multiplication and they're all common factor pairs, so I'll be able to remove those common factor pairs together. Now this 4 factorial, I need to actually write it out. That is 4 times 3 times 2 times 1. Since when I remove this common factor pair of the 11 factorials, the factorial notation is gone. So I need to make sure I have the separate factors that I can simplify. Now in simplifying these, you want to find common factor pairs between the numerator and the denominator. In this particular one, I see that 4 times 3 is 12. So 12 is a common factor pair with 12. And then for my other factor, 2 in the denominator, 2 goes into 14 7 times. And now when you multiply 15 times 7 times 13 and figure that value out, that's 1,365. Now another way to do that is on your calculator. So you're going to put the 15 in the open, just calculating screen, and then push the math button. And then you're going to cursor right to the PRB heading. And if you're on a TI-83 or TI-84, and then you go cursor down to the NCR option, push enter, and then put in your R4 and enter, and you again will see the 1,365 that we got by multiplying that out. So that's how many different ways a 4-member committee can be chosen from that club. Now the second one is where we start using what's really the focus of this video. It says how many 4-member committees can be chosen if the committee consists of 1 man and 3 women. So see how this is different? I have those subsets in my overall set, and I'm picking a few out of the specified subsets. So to find that out, that's when we're going to do this technique where it involves both the multiplication rule of counting as well as combinations. So when we're thinking about this, we want to think, well, how many ways can we select the 1 man out of the men that are in the committee or in the club, and then multiply that by how many ways we can pick the 3 women out of the women of the club. So for the first one, there are 7 men, so 7 men, combination, and I want 1 because it says you want a committee with 1 man. And then I'm going to multiply that by, so that's where your multiplication rule comes in, looking at the different ways you can select the 3 women out of the 8 women. So that'll be 8 combination 3. And when we multiply the 7 combination 1 times the 8 combination 3, you get 392. So we'll look at a few more examples so that you can kind of get the hang of this and then also use this within probability. The next example is how many ways can you select a 4-member committee, so it's still a 4-member committee, consisting of 3 men and 1 woman. So again, I know the subset that my overall set has been broken up into, and when they ask me for the counting technique question, they want me to answer it in how many different ways I can select so many out of the different subsets that they've identified. So when I'm looking at this, I'm going to have again the combinations that I use for making the selections out of the subsets, but then I need to multiply those together using the multiplication rule of counting to get the overall grouping of it. So we have our 3 men, there are 7 men, so it's 7 combinations 3, that's choosing 3 out of the 7 men, times, and then 1 of the women, so 8 combinations 1, and when you figure those out and multiply them together, you get 280. Now the next one, how many different ways can you select a 4-member committee that's consisting of no men? Well, you could actually say that I have 7 combination 0, because I don't have any men, times 8 combination 4, because if there's no men in the committee, all 4 of them are women. So I could do that and I would get the same answer just if I looked at it and say, well, it's going to be all 4 of them are women, so I can just do the combinations of 8 things and choose 4 of them. And we'll go ahead and put there's 7 combination 0 in front of it, but this value is just 1. So 1 times the 8 combinations 4 is why we could. When they asked me these different questions about this type of a problem, the setup could be exactly the same. And I have to read very carefully what they're asking me to do in the question, so I make sure that I don't jump into a process that isn't the one that's appropriate for that setting. Now this question doesn't say how many, it says find the probability that. So I know that my answer when they're asking for a probability is going to be a number that's somewhere from 0 to 1. And remember, for probability, if we're finding it from the classical approach, it's the number of ways you can meet the requirement that you're asked to find the probability of, divided by the total number of ways that it can occur, or how many are in the sample space. So when I think about the numerator for this probability, I want to think about the specifics of what they're asking me to find the probability of. And then when I'm thinking about the denominator, I just have to think of it as overall a 4-person committee. So our probability that the committee was selected at random will consist of 2 men and 2 women. Will be equal to the number of ways that you can have a committee of 2 men and 2 women divided by the number of ways you can have a 4-person committee. So first up, for the numerator, the number of ways of 2 men and 2 women on that 4-person committee. So for the numerator, it's going to be, there are 7 men, so 7 combination 2 of them you're choosing, and then you're going to multiply that by, you want 2 out of the 8 women, so 8 combination 2, and so we get that this is equal to 588, and then for the denominator, we're just looking at the number of ways to make a 4-person committee out of that total club. Well, there are 15 members in the club, so 15 members in the club, combinations, a 4-person committee, and that gives you 1,365. And again, if you want to use the formula, you can. If you want to use your calculator operations, you put the 15 in the calculator screen, math, prob, down to NCR, pick that and then put in the 4, enter, and you'll see the 1,365. So then when we go and make our probability of 2 men and 2 women is the 588 divided by the 1,365, and when I simplify that fraction, I get 28 over 65. So if you leave your probability answers in fraction form, and there's not other operations that you're going to do with it later that you would need to keep a common denominator sort of a setting, then leaving your answers in the simplified fraction is the best way to leave it. And certainly we could leave our answer to our probability as a decimal. Remember, if you're approximating your decimal for your probability, you should have it to 3 significant digits, unless wherever you're working and applying this to, it requires a different amount of significant digits. And then if you decide to leave it into your percent form, remember that if you change it into percent, to really put that percent symbol afterwards as well, so that you keep the value that it's supposed to have. So this probability is 28 out of 65. Let's look at another example. In this example, we're going to look at a quality control sort of a problem. So we have a shipment of 130 fasteners. And in that shipment, there are 5 that are defective. So somewhere in the shipment, within the 130 fasteners, there are 5 that are defective. Now the quality control department sends someone over and they randomly select 8 fasteners out of that shipment. And they take them in and they test them. What is the probability? So it wants me to do a probability question here. So I need the number of ways you can meet the requirement divided by the total number in the sample space. That, my first one is that no defective fasteners are in the sample. So again, we have our overall population that's been broken up into subgroups, and we're looking at the probability that we have so many out of each subgroup for our numerator, but in the denominator it's just pulling out of the entire group. So the probability of no defective, we're going to get from the fraction. Where in the numerator, we don't want any defective, so we're going to have 0 out of the 5 that are defective, so 5 combination 0 times, and if there's 130 fasteners in the shipment and 5 of them are defective, 130 subtract 5, or 125 are good. So that's 125 combination. And then if I'm picking 8 fasteners and none of them are defective, that means all 8 of them should come from the good fasteners, the ones that aren't defective. So that'll be 8. And then I divide that by thinking of the overall sample space of your 130 fasteners in general, and you're picking a sample of 8 out of that. So that is the setup of our probability. Now to calculate this out, you can either use the formulas that we did earlier in the video, or if you have a TI 83 or 84 or other calculators that have the options of combinations in them, you can go ahead and calculate it out. These numbers get big, but then when you divide them, you get to your probability value. So one thing you want to remember, that if you're going to go through this, to make sure that you grab the numerator in parentheses and then divide by the denominator, just to be on the safe side. So then what you get from this is 0.724. If we leave our answer in decimal with 3 significant digits, and remember your probabilities will come out to be a number from 0 to 1. So if you're not getting that, then you must have either set up the fraction incorrectly or entered it into your calculator incorrectly. And then if you want to work with leaving it as a percent, remember you're going to move the decimal point 2 places to the right and then put the percent symbol on it. So 72.4% chance of pulling a sample out of there where you don't have any of the defectives in them at all. How about the next one? Exactly 1 defective is in the sample. So the probability of exactly 1 defective, you're going to set up your fraction. So in the numerator, you've got to have 1 come from the defective group. So I have 5 combinations 1 times, and then again, if we have 130 fasteners all together, 5 are defective. That gives me 125 that are good. So I have 125 combinations. And if I selected 8 total for my sample, and I'm looking at saying, well, 1 was defective, out of that 8, 7 of them had to be good. So I'm going to choose 7 there. And again, in the denominator, it's the overall 130 fasteners combination, choose your sample of 8. And when you work that out, you get that's about equal to 0.245 to 3 significant digits, which is 24.5%. I'll just write them over here. And this other one was 72.4%. I changed it to percent. And now the last one. The last one says that at least 1 defective is in the sample. So when I'm looking at the probability that at least 1 is defective, I would, if I went straight away towards it, find the probability that exactly 1's defective, plus the probability that exactly 2 are defective, plus the probability that exactly 3 are defective. And I have to do this all the way up to the probability that all 8 are defective. And if it's 1 is defective, or if it's 2 are defective, or if it's 3 are defective, I would add those probabilities together. But the only situation it's not having to be within which makes this true, is if none are defective. So at least 1's complement is none. And I can find the probability of the complement by taking 1 minus the probability of the event, or I can find the probability of the event by taking 1 minus the probability of that event's complement. So when you look back at this first one, we found the probability already that none are defective. So if I want the probability that at least 1 is defective, I just need to take 1, subtract the probability that none are defective, and I get it straight away without having to do all those other calculations. So if I can find another way to come at it that saves me calculations, I'm all for that. So we're going to look at it this way. Our probability of at least 1 defective is equal to 1 minus the probability that none are defective. So that gives me 1 minus my 0.724. And that gives me 0.276. Or 27.6%. So hopefully you've been able to see a little bit of the pattern that is occurring within the types of questions that are being asked and then how you calculate them. And that will help you identify when this technique of using combinations within the multiplication rule is beneficial when we're looking at counting techniques, and then how we can also extend this to help us find the probabilities that incorporate those sorts of questions.